Now another important rule that describes ideal fluid flow is called Bernoulli's equation. It's named after the man who discovered it. So Bernoulli's equation tells us that the pressure plus half the density times the velocity squared plus the density times the acceleration due to gravity times the height is equal to a constant. Now Bernoulli's equation essentially comes about because of the conservation of energy in a fluid. I'm not going to derive this equation in this video, but if you are interested, there is a video which you can link to below where this equation is derived. So there's some interesting things that Bernoulli's equation tells us about. In the next video, we're going to look at what it tells us about giraffes. But here, let's consider if we had, like we had before, a wide pipe going into a narrow pipe. Now, to keep it simple, we'll say that these pipes are at the same height. So we can ignore that height term in Bernoulli's equation. And so we've got that the pressure plus a half the density times the velocity squared is constant. Okay, so we start off in the wide pipe. As we go from the wide pipe to the narrow pipe, the cross-sectional area A decreases. Now, we've just seen that A1 times V1, the velocity in part 1 of the pipe, is equal to the cross-sectional area in the second part of the pipe, A2 times V2. So as A decreases, V has to increase. So in the narrow pipe, the velocity is much faster than in the wide part of the pipe. And now what Bernoulli's equation tells us is that therefore the pressure in the narrow part of the pipe must be lower than in the wide part of the pipe. Let's have a look at a demonstration now to see if this really works. What we have here is a demonstration showing Bernoulli's principle. So in a minute we'll turn on the tap here, which will cause water to flow in from this end. Now here we have the wide pipe. So the wide pipe has the large cross-sectional area, and so the smaller velocity flowing through. And so if it's got a smaller velocity, it needs to have a higher pressure to make up for that. In the middle here, we've got a narrower pipe, so a much smaller cross-sectional area. And so we have the water flowing more quickly through here, and so we should end up with a lower pressure. And then let's see what happens to the end one here, where the cross-sectional area of the pipe is the same as at the beginning. Let's turn on the tap now. So you can see at this end, the little bottle rises to quite a high height, indicating that we've got more pressure at this end. Then when we go through the narrow part, this bottle rises to a lower height, showing that we've got a lower pressure in the middle here. Now, according to Bernoulli's equation, because we have the same cross-sectional area here as here, and the height is the same, the pressures here and here should be equal. So can you think, what is going wrong? Why are these two heights not the same?